Good morning, friends. Let's start with the new chapter of Introduction of Mathematics of Management. Started with the set theory, what exactly the set theory and how we will go ahead with the set theory. Set theory is basically we have learned in our mathematics. It's basically provide the relationship between the two sets. There is a two sets just like students and their subjects, and we have to provide the relationship between the students and their subject. So what exactly, how we'll go ahead with the set theory? In management terms, let's see over here. What is sets? Basically, a set is any well-defined collection of objects. Any well-defined collection of objects. Set we define in like oval shape. It is something oval shape. In the oval shape we have defined some objects just like a number. Any number you can say that just like a number of students, so 1 2 3 4 and their subjects like, or name of the students just like Ram, Shyam, and there is the subjects through which they belong, or name of the students and their class through which they belong. It's a relationship between the students and their class or their subjects like that, or the students and their college. Sets is something about that. We denote the sets with the help of curly braces. It's like A is equal to curly braces 1 2 3 4 5. It's a kind of set we are defining. Definition: element of sets are the object is a set. Notation: usually we denote set with uppercase letters. It's like capital A, capital. We never denote the set with the lowercase letters, so always use uppercase letter. Elements with the lowercase letter. The following notation has been used to show set membership. Just like here they have shown over here, means that X is a member. See, X, this is notation of relationship, a member. Just like this is the shows the relationship of X with A. So we can say that X is a member of set A, or this is the way we have denoting. So means the X is a member of set A. X is nothing but a set, a member, and this is the relationship of set. So X is a member of set A. It is showing over here. Then second one, the same thing. X is not a member of set A, means that X is not a member of set A, like that there. So this is the way we are denoting the set over here. And the set is nothing but a well-defined collection of objects, and this is the way we are denoting the set. So ways of describing set. So I have tell you that we are describing the elements. These are the elements. A is nothing but a set, and these are the elements of that particular set. So I can say these are the member of the set A. So A is equal to 1 2 3 4 5 6. So these are the elements which come under set A, and we denote the set A. If anyone wants to how to denote the set A, if they have a member of object 1 2 3 4 5, so this is the way we are denoting. So A is equal to 1 2 3 4 5. Give a verbal description. So A is a set of all integers from A to 1 to 6 inclusive. Inclusive in the sense 1 and 6 both are inclusive, both are there. We can use the term inclusive when we are using the term exclusive. Inclusive in the sense 1 and 6 both are, it has to be used under set A, element of set A. If they use the word exclusive, so we have to eliminate the word 1 and 6 over here. So because we are using it's inclusive, so A is a set of all integers. A 1 2 3 4 5 6 is nothing but an integer. So these are the integer of the set A. So as you know, the 1 2 3 4 5 is number, which is also known as integer. So A is all set of so A is a set of. So in the text or verbal description, how you denote the A is equal to 1 2 3 4 5 5 6. So how you denote these things? So in a verbal description we can say that the A is a set of all integers from 1 to 6 inclusive 1 and 6 are over there. And the mathematical, give a mathematical inclusion rule. So we can see that a is equal to integer x, where x belongs to 1 to 6, which is 1, x belongs to greater than 1 and less than 6, and this is a sign less than equal to, this is a sign, this is a sign less than equal, so x is greater than, so it is greater than is equal to x, and x is less than equal to 6, so this is less than equal to, this is sign of less than is equal to, this is also because this is x over here, and here I can see that x minimum number is 1 and maximum is 6, so x, the value which is greater than 1 and lesser than 6, so this all denote this is like this. In the mathematical terms, the same thing what we have seen over here. If you want to describe this a is equal to 1 2 3 4 5 6 in the mathematical term, so we have to show like that a is equal to integer x, x is nothing but 1 2 3 4 5 6, where x belongs to 1 2 3 4 5 6, like that you can show. And the same thing we have seen, we can show like this, x belongs to 1 to 6. Some special sets, there is some special sets which we are going to discuss over here. The null set or empty set, this is a set with no elements, often symbolized by this. Actually this set which has no element, which is a zero element, I can say that, which is empty set. Empty set in the sense which has nothing, there is no elements belongs to that particular set, which is called the null set or empty set. There is two word has been used over here, null set or empty set. Just think like that the set which has no elements. In the previous slides we have seen that the element set A have some element over here. This is the integer value from 1 to 6. But in the next slides we can see that the set which has no value, that particular set is called a null set, which is denoted by this, like this. And then we can say that the universal set, this is the set of all elements currently under consideration, and it is often symbolized by this. This is a symbol of universal set. This is the universal set, which is set of all the elements. This is the set of all the elements. So this is especially there is nothing I can say that restriction. So it is a set of all the elements which is called the universal set. So definition of subset, member, this is a member relationship of sets, definition subset. So we are seeing that it is written over here in the verbal communication, A is subset of B. A is subset of B. How we denote that? So A is subset of B. This is the denotion of the subset. This is denotion of the subset. We can define, if we in the mathematical term or set theory term, we can written right there like this, A is a subset of B. So whenever this symbol you will find anywhere, so just keep in your mind how will denote in the verbal, my mind to say in the text, how will write this text. So A is a subset of B, which is written in the left side, which that is a subset, and which is written in the right side, that is a set. So A is a subset of B. How we say that? We said that A is a subset of B if X is a member of A and X is a member of B. So we can say over here the A is a subset of B means X is a subset of A as well as the X is a subset of B. So X belongs to both A and B. Here the X belongs to both A and B. So X is anything. So that is all the member of A are also the member of B. What is the meaning of this? If one belong to A, suppose X is equal to 1. So if one belong to A and the same one belong to B, so one which is 1 belong A and B both. So one is a member of A as well as B. So we can say that all the members of A are also the member of B, which is very true, because one belong, if I'm taking X is equal to 1, I will give you an example over here. I can take one. One second, I will take one. notepad. I need a notepad. See, if we say that A has some set, how we are denoting the set? We are denoting the set like this. So A is a subset like 1, 2, 3, 4 and 5, and B has some value. B is like the same 1, 2, 3, 4, 5. So I have taken X, which is equal to 1, 2, 3, 4, 5. So I can say that X, I have no that kind of denotation over here in this. So I'm written like this. I can say that X is, because I don't have a denotation like that, so I've written like that X is a member of A, X is a member of A, and the same X is member of B. So if, see, you can see that X has a 1, 2, 3, 4, 5, which I have shown over here. So A is nothing but equal to X over here, we can say that, and B is also nothing but we can say that X. So A is also X and B is also X. So A belongs to X, X belongs to A and X belongs to B. So obviously the A and B both belong to the same set. So this is written over here, the same thing written if X belongs to A and X belongs to B. So all the member of A are also member of A are also the member of B. The notation for subset is very similar to the notation of less than or equal to. See, which is we are saying less than or equal to sign. How we denote the less than equal to sign? We are denoting the less than equal to sign like this, like that. This is the notation of this notation. This is the notation of less than or equal to, and means in terms of sets include, in or equal to. So we can say that it is include or equal to. Then we have a proper subset. Proper subset. So how you denote the proper subset? So denoting the proper subset, we are write like A is a proper subset of B. This is the proper subset. Here we have denoted the subset over here. This is also a subset. This is the subset. But when you are asking for the proper subset, we are taking this kind of symbol, the equal to symbol, which is written over here in the subset, which is eliminate over here. So we have seen only proper subset. So A is the proper subset of B. So A is the proper subset of B. So we have denoted like that. A is the proper subset of B. We say A is the proper subset of B if all the member of A are also the member of B. The same thing which I have seen over here. If all the member of A is also the all the member of B. So here we can see that X is a member of A and X is a member of B also. So A is a proper subset of B if all the member of A are also the member of B, but in addition there exists at least one element C such that but the notation of subset is very similar to the notation for less than and means in terms of a set included it but not equal to. Here we can see that C is a subset of B, C is a member of B, but C is not a member of A. There is a one element in both the terms which is not belong to one another particular value. Just like here, sorry, I can say that if I'm going to reduce this, so A have a 1 2 3 4 5, A have a 1 2 3 4 5, and B has a 1 2 3 4. So A, so 5. Here I can say that 5 belong to A, but same time 5 did not belong, I will cut like this, did not belong to B. Here you can say that 5 is belong to A, but 5 is not belong to B. So here we denote that A is subset of B. A is the proper subset of B. Like this we could denote over here. So A is a proper subset of B, like this. Then union, we have a union. How we denote the union? This is the U operator, which is shown over here. This is the U operator, A union B. So A union B is a set of all elements that are in A or in B or both. So this is similar to logical or operation. How you denote the A union B? I will show here. Suppose A have this much of members, 1 2 3 4 5, 1 2 3 4 5, and B has only 1 2 3 4. So how you denote the A union B? So A union B, when I'm going to denote A union B, when you're going to denote, so you have to take all the member of A and all the member of B. So all the member of A, 1 2 3 4 5. So A union B will come 1 2 3 4 5, in which we can see that B have a 1 2 3 4. So we have taken 1 2 3 4 over here, and B has, A has a 1 2 3 4 5. So A 1 2 3 4 5 has come. So all the member of A and B which is belong come under A union B. So you understand, A union B has all the elements irrespective to either they have in the another set or not, but we have to take in the A union B. Another example for A union B, suppose A has 1 2 3 4 5 6 7 8 9, okay, and B has only 1 2 3 4 5. Suppose A has a 1 2 3 4 5 6 7 8 9, and B has a 1 2 3 4 5. So A union B, when we are going to ask for A union B, it is like 1 2 3 4 5 6 7 8 9. Why 1 2 3 4? Because A union B, I need all the elements which belong to A and B both. So here I can see that B have 1 2 3 4 5. So I have a 1 2 3 4 5, and A has a 1 2 3 4 5 6 7 8 9. So I have a A 1 2 3 4 5 6 7 8 9. So in the union we required all the member of A as well as all the member of B. So you understand these things. Now A union B we have done. So A union B is a set of all elements that are in A or B or both. This is similar to the logical or operator. This is similar to the logical or operator. Then A intersection B. What is the meaning of intersection? So intersection says if A intersection B is a set of all elements that are in both A and B, which is similar to the logical AND. So A intersection B, in the A intersection B, we will take those values which are in common in A and B. Let's see with example. So here I can say that, see, A union B we have taken 1 2 3 4 5 because 5 is also over there. But in A intersection B, how will denote or intersection over here, because we have to denote like this. So we don't have anything. Suppose I am denoting like this: A intersection B is equal to, I have to take the common words in A and B, either one, either this or this. So I have to take the common one. So if I am going to take the common one, so 1 2 3 4, this is the common. 5 is not there in the B, so I have eliminated the 5 for A in A intersection B. But in union, because I have to take the combined value of A and B, so I have taken 5, or 5 have to be there. But in intersection, I have to only take the common value in A on B. So that's why I have taken only 1 2 3 4. Again, I will take the one example. If A has 1 2 3 4 5 6 7 8 9, suppose, and B has 1 2 3 4 5 6 7, suppose. So A intersection B is like what we are going to show in A intersection B. So A intersection B, I need the common value from both. So I have seen that in the set A we have a 1 2 3 4 5 6 7 8 9, and in the set B we have 1 2 3 4 5 6 7. So common element is 1 2 3 4 5 6 7, which has 7 till 7 value in both the sets. So common element will be 1 2 3 4 5 6 7. So this is the common element. So A intersection B is nothing but 1 2 3 4 5 6 7. This is the common, which is AND. So you have seen that A intersection B intersect B, which is A intersection B or intersect B, whatever you want, you can denote over here, is is the set of all elements that are in A and B both, so which are in common. This is similar to logical AND. And A bar, which is called A bar. A bar means not A, a complement. A complement. A bar is nothing but which is called, it is a complement set which is nothing but denoted by A bar. This is A complement or not A, which is also called not A. Is the set of all elements which is not in A. So the complement operator is similar to the logical not, and which is reflected, that is A double bar is equal to A. One I am going to take bar and another time no bar, which is going to A. Let's see the A bar. A bar meaning which is not equal to A. If A is this, so A bar in the sense, if I am going to check A bar, so A bar over here is equal to, which is not equal to A. A bar is not equal to A. A bar is meaning is not equal to A, which is not equal to A, which is called the A bar, or not equal to set, not equal to A set. So A bar is equal to, so A bar will denoting like this. So A bar equal to, which is not belong to A. So I can say 6, which is not belong to A. I can take any value not belong to A. It is like that we are showing, denoting the A bar. Then we are going to check A minus B. It's a different set. Difference. We show the difference. So the set difference A minus B is the set of elements that are in A and those that are in B subtracted out. So another way of putting it is set of elements that are in A but not in B. So A bar we will going to say like that, A minus B. So I can say that like, see, this is B. So set of A minus B equal to, which is in A but not in B. So only 5 will come over here. Why only 5? Because 5 is not there in B. So if I'm going to minus this, so this will cut, this will cut, this will cut, this will cut. Only 5 will not cut, because 5 does not have in the B. 5, the value of 5 is not there in B. So this will cut, this will subtract, this will subtract, this will subtract, this will subtract. Only 5 is remaining. So 5. This is 5. If suppose I have removed the 5, so it is become A minus B, which is become null set. Null set, which is denoted by O, and this is like this. You know that how we are denoting, because I'm not able to denote over here, so it is called null set, because A and B are the same, so it is 0 value find over there, so it is become a null set, A minus B. So next is example. So this is a union A1 2 3 4 5 6, A1 2 3, A1 2 3 3 4 5 6. So union of A A intersection B. So you can see that here 3 is a common in intersection. 3 is a common. 3 is common. So intersection B is in both in these two, 3 is common. So 3 is here. A union B, I can say that 1 2 4 1 2 3 4 5 6. So 1 2 3 4 5 6. B minus A, in the B minus A I can see that, so 3 is there, only 4 5 6 will come. So 4 5 6 has been B bar, which is nothing but, so B bar. So in the both I can see that B bar is like B minus. So in B bar, union is 1 2 3 4 5 6, but 3 4 5 6 has been gone from here. Union, you have to see the union. In the union 3 4 5 6, and the B is 3 4 5 6. So 3 5 4 5 6 is cut over here, and 1 2 is remaining. So B bar is equal to 1 and 2. It is like that. So Venn diagram. Now we have come to the Venn diagram, which is very much important. Venn diagrams, when you are going to work some mathematical terms in your management side. So Venn diagram is very useful in different scenario. Venn diagram basically used in the different scenario, in which we denoting the different sets, we denoting the different numbers, we denoting the cells, we denoting the marketing, and we denoting the advertisement. All these things, when you are sometimes we are going to denote with the help of Venn diagram also. So Venn diagram we can see over here. So how to denote the Venn diagram, we will see over here. So Venn diagram, when you are going to denoting the Venn diagram, basically we are denoting the Venn diagram with the help of, one second, I will take one example. One second. What I need, word. See, word. I require a word. See, in the Venn diagram, how will show the Venn diagram? I will show you. See. Basically, we are going to Venn diagram with the help of two circles. This is the Venn diagram, and when and to denote this inside a box. So this is the Venn diagram. We are denoting the Venn diagram like this. So in the Venn diagram, what happened? We have taken one box. Inside the box, we have taken the sets, This is the set A and set B. This is like this, set A and set B. In the while we are denoting the sets, we are denoting with the two circle, just like shown over here. It is denoting with the circle. So this is the two circles, set A. This is called the set A, and this is the set B. How you denote the set A and set B? Like this. So if you want, I can write. We can write over here. Forget that. Just be think that this is set A and this is the set B. So how you going to write in the set A? How you denote the set A and set B? Suppose I want to show you A and intersection B. So A intersection B, how you denote that? In the A intersection B, what happened? We have to take the common values from the set A and the set B. So how you going to denote? For intersection, what I need to do? We need to put like this. So this is the common value over here, the value which is come over here. So I'm going to take like this. So this is the common value. You can see that this is the common value over here. This is the common value in both. We will take copy this. Some find I can. So you can see that over here. This is the common value. So this is the common value in both the areas. This is the set A and this is the set B, and this is A intersection B. So this is the common value which is ruled over here. So this is the common value in both the circles. So this is called the A intersection B, which we have seen over here. This is the A intersection B. Again, the Venn diagram, try this like that, A union B. So A union B will come all the values which is belong to A as well as in B. So we can denote like this. So A in the A union B, the value which is intersected as well as the value which is surrounded over here will all come. So A union B is like this. So this is called the A union B. So entire value of A which is either belong to A or not, or B or not, and entire value of B which is either belong to A or not, which is club, is showing to the A union B. So A union B will give you all the value of A as well as all the value of B. So A union B belong to all the value which is either belongs to or not, that doesn't matter. So all the value of A will come over here as well as all the value of B also come over here. So A union B like this. So this is A union B, and again we can see that here is another one, A minus B. In the A minus B, what we need to do, the value which is in A and B, so which is not in B, we have to take only those values. So A minus B, something denoted like this only. So how you denote the A minus B? I have shown over here. If I am going to take 5 over here, the value of A minus B, you will get only 5, because 1 2 3 4 has been cut through here, 1 2 3 4, and only 5 is there, so 5 belongs to here. So A minus B equal to 5. Only 5 is there, only 5. So only 5 will be showing over here. Only 5 is here. So A minus B only 5. A minus B will come only 5. So A minus B, only 5 will come over here. Mutually exclusive or exhaustive sets. Mutually exclusive or and exhaustive sets. So definition, we say that a group is set of exhaustive of another set if their union is equal to that set. For example, if we say that A and B are exhaustive with respect to C, so this is like this. So definition, we say that a group is a set of exhaustive of another set, exhaustive of another set if their union is equal to their union is equal to that set. For example, if we say that A and B are exhaustive with respect to C. I will give you the example so you understand very well. If I want, see, if I'm going to take A union B over here for this given set, if I'm going to take A union B, so it is like 1 2 3 4 5. A union B is 1 2 3 4 5 because 1 2 3 4 5 is in the A set A and 1 2 3 4 is in the set B. So if I'm going to club both, so 1 2 3 4 5 will come over here in the union. And if I'm going to take C, if C is also equal to 1 2 3 4 5, if C is equal to 1 2 3 4 5, so this is called the exhaustive set of. So here I can say that A union B is equal to C. So A and B are exhaustive set of set C. The same thing written over here. If we say that the group A set is exhaustive to another if their union is equal to that set. For example, if we say that A and B are exhaustive with respect to C. So definition, we say that the two sets A and B are mutually exclusive if that is, if the sets have no elements in common. So if I am going to take this example, suppose I have taken 5 over here only. In the set A I have taken 5, 6, 7, 8. If I have taken 5, 6, 7, 8, here I have taken 1, 2, 3, 4. So what is the so here what we are taking A intersection B. So in the A intersection B, because when we are going to see A and B, set A and set B, there is no common. In the 5, 6, 7, 8, 1, 2, 3, 4, there is no common. So which is come null set. So when A intersection B is come to the null set, so this is called exclusive. This is exclusive. So here is exclusive and this is exhaustive. What is that? This is exhaustive. H-A-U-S-T-I-V. H-A-U-S-T-I-V. Exhaustive. This is the exhaustive set and this is the null, exclusive and this is exhaustive. This is the simple. In the one case we are taking the intersection and the exhaustive. Do remember, in the exhaustive we are taking the union, and when the exclusive we are taking the intersection. That's it. Exclusive, intersection, and exhaustive we are taking the union. It is very simple. Then set partition definition. We said that the group of set partition another set if they are mutually exclusive and exhaustive with respect to the set. When we partition a set, we break it down into mutually exclusive and exhaustive region, that is region with no overlap. The Venn diagram below should help you get the picture. In this diagram, the set A, the rectangle, the set A, which is nothing but a rectangle, is partitioned into set W, X and Y. Let's see. W, X and Y. Some basic rules of differences. So now start with the difference. So we have done Till now we have done with the I can say that the set. In the set we have learned what we have learned. We have learned about the here we have learned about the set theory. What exactly the set theory? We have learned about the sets, how the sets, how it is work, different sets. We have learned. We have learned what exactly the sets, how we denote the sets in the mathematical terms as well as in value. I mean to say in the text form, how we verbally denote that. Then third thing we have learned about the different kind of their I can say that their intersection, just like they have a union, intersection, they have their notation. We have learned we have learned the union, we have learned the intersection, we have learned the bar is like not equal to, which is a bar, b bar. We have learned the difference of set a minus b. Then again we have learned the exhaustive set in exclusive set. Then we have learned the null set. So these much things we have learned till now. In the another, we are going to learn the differentiation. What exactly the differentiation? How we denote that? We will learn. So we have done the set theory. The set theory basically we have used in the management rule. Sometimes when the requirement has been come. So let's start with the basic rule of what exactly the differentiation. So differentiation is nothing but basically we are using, it is very old mathematics which has come in the calculus. So basically differentiation and integration is about to denoting any function. Basically the function, how you can solve the function with the help of these terms. So we are basically going to solve some function with some formula. On the basis of formula, we are solving some quadratic equation and after quadratic, then trigonometric, and the x to the power 3 equation or 4 equation, like that we are going to solve with the help of differentiation, and the same thing we can solve with the help of integration also. Let's start with the differentiation and integration. At least you can understand. I'm not going to give you the whole funda because we don't require to go inside a mathematics and we will learn each and every topic about the differentiation and integration because it's a very huge one. So what my funda is, at least the basic concept you can clear. If the question, I mean to say, if somewhere they have solved the differentiation terms or integration terms, so you can understand how it is solved. All these things we can learn. So let's start with the basic rule of differentiation. So basic rule of differentiation. Using the definition of the derivative can be tiresome. So in this lesson we are going to learn and use some basic rule of differentiation that are derived from the definition. For these rules, let's assume that we are discussing differentiable variable. So this is the formula. F dash x is equal to, this is called limitations. Limitation h belongs to 0, f of x plus h minus fx upon h. This is the basic formula which is you have to understand. So you can say don't need to mug up, just keep in your mind. So f dash x is equal to, limitation is nothing but we are putting the value of 0 here. If initially we are going to put the value of 0 over here, so you see that there is something upon 0 which is nothing but, so 1 by 0 is nothing, which is kind of infinite. So infinite is nothing. So basically we are starting over here, so we are putting different value here and there, and we are getting the result of differentiation. So you can see that derivative a constant. Always do remember, derivative of any constant will be 0. So here we can see that dc upon, this is the derivative. How we denote the derivative? Basically we are denoting the derivative like this. So dc upon dx is equal to 0. So for any constant, if you are taking any constant, their derivation will be 0. The rule states that derivative of a constant is 0. For example, fx is equal to 5 and f dash x is equal to 0. 5 is nothing but a constant value, so their derivative will be 0, like this. So another rule 2, d of x to the power n upon dx, which is nothing but what we will going to do. What is the power is there? Whatever the power, see x to the power n. So what we need to do, the power will come when you are going to solve this. So power will come over here n, and x to the power n minus 1. It becomes x to the power n minus 1, where n is any real number. This rule states that the derivative of x raised to a power is the power times x raised to a power n less than or n minus 1. For example, so fx is equal to x to the power 5. If x to the power 5, when you're going to solve this, so 5 will come according to this rule, fx to the power 5. So according to this rule, 5 will come over here. So 5x, 5 minus 1 over here. So 5x to the power 4 has to go. 5x to the power 4. Notice the derivative is the original power. 5 times x raised to the 4th, which is less than 5. So how you define this? So if you are going to solve this question like this, so we have to solve like, so d of x to the power 5, we are going to x to the power 5, sorry, we are going to x to the power 5 upon, suppose, dx, how you solve this? We are going to solve like 5, what is the value? It will come over there 5, then x to the power 5 minus 1, x to the power 5 minus 1. So it is shown like 5 x to the power 4. 5 x to the power 4. This is the equation, simple the way we are denoting. This is called the simplest way to denote this. So 5 x to the power 4. So notice that. So anything which is belongs to like this, so we are going to denote this like this. So the power which is there, which has come out over here, and the minus 1 has been deducted, so 1 has been deducted from the power, so it has become 5x to the power 4. So derivative of a constant multiple of a function, we can see over here, when you're going to derivative of any constant with the help of the function, multiple function, so here it is denoted d upon dx c fx. Fx is nothing but a function, so d by dx c fx. So what I will do, c I will take out because this is a constant, so c I will take out. So my denotation becomes d fx upon dx. So d fx upon dx. C I will take out. Constant always will come out. So c d by dx fx. So if fx is not there, suppose fx is not there, so dc by dx is value which is always 0, which we have seen here. So dc by dx, you can see that this is the constant, so always dc by dx is 0. And here, because we have the function over here, so dc by dx, so c we will take out, so d fx upon dx, where c is a constant. So fx is equal to 5x to the power 4, which we have seen over there. So the rule states that the derivative of a constant times a function is a constant times the derivative of a function. For example, find the derivative of d by dx fx 5x to the power 4. So what I will do, again here just see d by dx 5x to the power 4. So what I need to do, the 4 is again come over here. So d by dx x to the power 4, because this is a constant, 5 is a constant, so it will come over here. So 5 d by dx x to the power 4, 4 is there, 4 again will come over here. So 5 4x to the power 3, which is nothing but 20x to the power 3, like that. This is denoting, it is very much simple, there is nothing. I will show you again. So formalize this d by dx c fx. So when the c fx is there, c we will take out. So d by dx fx is there, function, this is the function, so we need to derive this. So it's the same thing. So d by dx fx, so d by dx 5x to the power 4, see the same thing over here, because 5 is nothing but a c constant. Suppose this d by dx c fx, so d by dx c, this is the fx function. So 5 I will take out, so 5 I have taken out just like here. So now d by dx fx, so d by dx x to the power 4. So what I will do, 4, because in the previous denotation we have seen that formula is n x to the power 1. So the same formula we are applying over here. So 4 will come over here. So 5 is there. So in the bracket we will put 4. 4 minus 1, because here we have seen that x n minus 1. So we can see that 4 minus 1 is 3. So 5 into 4, which is 20 x to the power 3. This is the simplest way we are doing the mathematical. So derivative of sum or difference. So there is some derivative of sum or difference. We can see. So here derivative of sum and difference. So this is the sum. So derivative of sum. When you are going to derivative of sum, so d by dx fx plus gx. So we have to apply for each and every function over here. So you can see that fx. So d by dx into fx plus d by dx into gx. We are applying the both. So d by dx actually the multiplied with fx as well as for gx. So this rule states that derivative of sum or difference is the sum or difference of the derivative. If in place of plus, if there is minus, so we have to apply derivative in over here. So after that, for example, so derivative of this, I have told you we need to actually sometimes need to find out the value of quadratic equation. So x square plus 2x minus 3. So what I will do, so d by dx, again d by dx is x square plus 2x minus 3. So d by dx I will multiply it with all these values. So d by dx is x square plus d by dx into 2x plus d by dx, this is the minus, so minus plus minus minus, this is minus over there, d by dx minus 3. So it will be shown over. So d by dx is x square. Again we have to apply the same formula what we have seen over here. So this is just like fx x to the power 5. So same formula we will apply over here. So d by dx x square. So 2 come over here, x to the power 2 minus 1, which is x to the power 1, which is nothing but a x. So 2x over here. So d by dx is 2x. So 2 I will take out because this is the same thing, cfx. So c I will take out, then dd of fx, dd